want a title, this is the, you can call it, I'll do notes in a second, but I'm gonna start by explaining like the overall concept with Desmos up here. You can call it definite integrals, or you can call it the fundamental theorem of calculus. Pretty good. Fundamental theorem. Or you can not put a title, but I'll let freaks you out. Okay. This graph is y equals the square root of x. So what is being demonstrated here? We're going from 0 to 9, and we have 9 rectangles. So this would this be a right-hand sum or a left-hand sum? Right-hand rectangles or left-hand? It'd be right. So what I did was 0 to 1 is my first interval. I went up to on the right-hand endpoint, went back across, pretended that was the height the entire time. So your base was 1, your height was 1. Your base was 1. Your height is, the square root of 2. Your base is 1. Height's the square root of 3. I'm not going to do them all. Just one more. I'm not going to do anything. There. Base is 1. Height square root of 4. Which is 2. So we talked about what would happen if I made more rectangles. Would the estimate get more accurate or less accurate? It would be more accurate. So what is really happening, instead of putting numbers there, could I write it like, or I'm going to write it like this, we'll see if you understand it. This width, I'm going to call dx. So every time this width is dx. And this height is f of x. If I plug in 1 into the equation, I'll get a y back. This height is f of x. This height is f of x. So aren't I just adding up a bunch of rectangles where and I can make this whatever I want. In this case, what is dx? 1. And the height, well, I plug into the equation. But if I made the rectangle smaller, what would happen to dx? If I made them narrower, what would happen to dx? It gets smaller. Could I make dx 0.5? Could I make it 0.1? Could I make it 0.01? Could I let the size of dx approach, but never actually get to 0? How many rectangles would you have in that case? An infinite number, which would be not an estimate anymore, but the actual answer. So this would be written as the integral from 0 to 9 of f of x times dx. And this notation is just, this is the height of every rectangle, and this is the width. The S stands for sum. So you are adding up a bunch of area rectangles. You don't have to write anything down, just listen. I'm trying to show you what the dx means, and I'm trying to go from doing rectangles to doing actual integrals. So what I can show you on here is if I made more rectangles. So now I'm going, okay, now there's 50 rectangles. Let's do this. Now there's 18 rectangles. What's dx now? 0.5. Because you got 9 units, you got 18 rectangles, so they're 0.5, right? And then you just have more rectangles, so you're getting more accurate. Now there's going to be 36 rectangles. What's dx now? 9 divided by 36, or 0.25. 90 rectangles. What's dx now? 9 divided by 90, so 0.1. And this only lets me go to 100, but I think you're getting the idea. If I let that go to infinity, wouldn't it be just basically the curve? Yeah. So that's what integrals are. You're taking Riemann sums, you're taking these rectangles, and you're just making an infinite number of them. And then that dx becomes infinitely small. So that's the test. If you're taking stats, there's the first 2 questions. 3 questions. Too late. So, definite integrals. Or FTOC, fundamental theorem of calc. Did you come to listen to the fundamental theorem of calc?
No, I'm good on that.
You're all set? All right. Thank you. So, a formula for this, if I have from A to B, so in that last example we just did, that was the 0 and the 9. Get that?
Yeah.
And there's kind of two ways to look at it. When you take the derivative, like if I start with f, and I take the derivative, what do I call it now? I call it f prime, right? So I'm going to put f prime in here. When I integrate f prime, where do I end up? I end up with f. So it's kind of weird because we're like starting at the derivative. You don't necessarily have to be at the derivative. It's just, I'm just trying to demonstrate that when we integrate, you go a level back up the chain. Derivatives take you down. Integrals go up. So the integral of f prime of x times dx, let's say. A is the left-hand boundary. B is the right-hand boundary. F prime of x gives us the heights of each rectangle. Dx gives us the widths of each rectangle. And then we let dx approach 0. It'll never be 0 because if the base of your rectangle is actually 0, you don't really have a rectangle. But it's going to be so freaking small that it might as well be 0. Then we have an infinite number of rectangles. So we solve this, and then what it finds for you, you're going to integrate f prime of x. So that you're going to integrate f prime. So if I integrate f prime, what do I end up with? F. And then this is my notation, and not everyone's is the same. This is what I recommend. It's easy to mess up if you don't. You don't necessarily need this bracket, but I think it really helps to put both brackets. The B and the A are still there, and what you do is you plug in B minus, you plug in A, and then that tells you the area between the curve and the x-axis. So we'll do a few examples, obviously. There's a lot there. Like just that one slide is pretty significant. But it'll be fine as we keep going, I think. Questions on anything I've said? Yeah? Okay. So, let's say that I gave you the integral from 0 to 3 of x squared times dx. So if I sketched that, this would be 0, this would be 3, and what I'm looking for is that area. So like the last couple of days, we would estimate it with rectangles. We'd have like 3 rectangles, maybe 6. That's I think through that process, if you imagine this were f prime, what would f be? So if you integrate x squared, what do you get? You get 1/3 x cubed, right? Add 1 to the power, multiply by the reciprocal of the power. From 0 to 3. You don't need the plus c in this kind. In the definite integrals, you don't need plus c. I'll show you why in a second. Basically, you get 2 of them and then cancel, but I'll go through that. Then you plug in the top number. So 1/3 times 3 to the third minus 1/3 times 0 to the third. Then you work that out. So what's 3 cubed? 27. A third of that is 9. Minus, and then that's nice because it's 0 to the third is 0. 1/3 times 0 is 0. So your answer here would be 9. So there's 9 units of area in that little kind of, but not quite, triangle there. And this process is all you have to know how to do today. Like we're just going to go through a bunch of those. Let me show you real quick why the plus c disappears. So imagine there were a plus c here, and imagine there were a plus c here. But when you went to plugged in, what's c minus c? So it just goes away. So if you wanted to write 9 plus c minus 0 plus c, I mean, there's no need to do that. So c's just cancel. They're technically still there. We're not just like forgetting about them, but they just go away. Questions on that process there? Go through this again. Do this. See where I'm at? Oh, there's test again. Let's say the integral from -4 to 4 of, let's just do x times dx. So I'm going to graph these for now. You don't really need the graph to do the problem, but we can. What does y equals x look like? Please don't say the word straight in your answer. What's y equals x? What'd you say? Wow. Slope of 1. What's the word that describes the thing that has a slope of 1? Vertical doesn't have a slope of 1. Starts with an L. 4 letters. It's a freaking line! God! That's all it is. Y equal, how about this? 1x plus 0? Does that make it make more sense? I don't know. So, I mean, if we just think through our answer here, I didn't draw this perfectly, but you'd be finding this area, and you'd be finding this area. This area will come out positive. This area will come out negative. So below the curve, a negative answer doesn't mean that you have a negative area. You can't have a negative area. Negative means you're below the curve. So won't these two be the same? So the integral, what should the answer be? Should be 0. This part above the axis and this part below the axis should exactly cancel out. So, I mean, just so we know where we're going, like, let's make sure we get there. So what's the integral of x? 1/2 x squared. Going from -4 to 4. You guys right? You sure? Okay. Still blown away by that line thing? So, maybe I didn't ask the question very well, I don't know. So you plug in the top number, and I would put these brackets there every time because you can really screw up the subtraction. You know, you're subtracting the whole quantity, so that does make a difference. minus 1/2 negative 4 squared. So what's 4 squared? 16, half of that's 8. What's negative 4 squared? 16, half of that's 8. 8 minus 8 is 0, which we kind of already knew, but I'm just showing you like how it works and why it matches up. Questions there? What's a line? Let's say negative 1 to 3 of 2x minus 4. Times dx. You want to put that part in parentheses because if you don't, you're really just multiplying like the negative 4 times the dx. And you want this to be like the base of the rectangle times the height of the rectangle, so the whole thing in parentheses times that. I need parentheses before because there's just like one thing there. So if I graph this, again, we don't need to, but I'm just trying to get you an idea of what they look like. I'm terrified to ask these questions now. What is the y-intercept? Yes. What's the slope? Awesome. You guys are all stars. Yeah, what kind of graph is it? A line. And I'm looking from negative 1 to 3. So this part, so this part. So this part's all below the axis. And this part's all above. So do I have more area below or above? Below, so my answer should be negative, right? Because I've got more of the graph below the axis than above. And with this, like, could I just use area of triangles and find this area? Yeah. But if I give you, sine of x squared, can you do that? It's not going to work anymore. So that's why we're trying to do this. That's why we're trying to do the process. So what's the integral of 2x minus 4? X squared minus 4x, right? And then, like, technically there's a plus c. I don't need them indefinite integrals because the plus, you'd have a c minus c eventually and they would just go away. Put your negative 1, put your 3. And then you always plug in, it's always top minus bottom. There's a couple things we do, like going through like the rest of the year. Top minus bottom is a theme. It's always top minus bottom. So I'm going to plug in 3 squared minus 4 times 3. This is where I definitely want to see you put that bracket there, because if you don't, you're going to mess up your subtraction. You with me? See what I'm doing? Yeah.
Why is it x squared minus 4x and why is it like instead of 1/2 2x? Why don't you do the chain rule thing because it's in parentheses? So why don't you do the?
Oh, like big guy, little guy?
Yeah.
What would your big guy be? Okay.
Would it come out to the same thing once you simplify it?
Yeah. So you're gonna go like that. This is your big guy. This is your little guy.
Yeah.
So the derivative of the little guy is, can I just say it will come out the same and skip all this?
Yeah.
Is that fair?
Yeah.
It will come out the same.
Okay.
You don't need chain rule because you don't really have a big guy, little guy. Like a 1 isn't really a big guy, it's just kind of there.
Okay.
Is that fair?
Yeah.
Okay. Any other questions? What?
I just screwed up the order.
You did bottom minus top?
Yeah.
Okay. So that's not a question, you just know. Yeah, so it's always top minus bottom. So, you have 9 minus 12 minus 1 plus 4. So it'll be negative 3 minus 5. So you guys get negative 8. So that means there's 8 more units below the axis than above. Questions there? So for today, we're just doing these. Like there's not going to be any reverse chain rule. There's not going to be any trig. There's not going to be any e's. Today, I said. And then I'll slowly start x squared. This is totally separate. This isn't even a lesson anymore. Lesson's over. I'm done. And it was midpoint with 3 rectangles, right?
Yes. Yeah.
So this was on the comp. We're just backtracking because she had a question. I figured other people might too, so I'm going to go through how to do that. So normally, I would set this up and I'd go, okay, that's 1, 2, 3, 4. But it gets goofy because it's midpoints. So for this interval from 1 to 2, if I were doing the left-hand sum, A and B, what letter would I use for the y value if I'm doing the left-hand sum? A, right? Because that's the left-hand endpoint of that interval. If I were doing the right-hand sum, what would I use? I would use the B. The midpoint is like a whole separate ballgame. I basically have to draw a new chart and say, okay, well, what's the midpoint of 1 and 2? 1.5. What's the midpoint of 2 and 3? 2.5. 3 and 4 is 3.5. And then plug in, so 1.5 squared is 2.25. 2.5 squared is 6.25. 3.5 squared, I think is 13.25. Someone check that. 12.25? Thank you. So when you go to do this, like what's the base of this rectangle? It's still 1, but what height are you going to use? Is this 2.25? So what's the base of this rectangle is 1, and then you multiply by the 6.25. And then the base of this rectangle is 1. And use that. So you're not using the value at one of the endpoints, you're using the value in the middle. So your chart gets goofy. Or think about it like this. That's 1, 2, 3, 4. So this distance, this base is still 1. And then that's your height. This distance, you know what I mean? Does that help? Okay. Alright, let me get you your worksheet and